All right. Starting off on chapter 13, gonna talk about functions of several variables. So up until now, everything that we've looked at has concerned vectors. And while they are important and definitely will come back for the last part of the course, we're going to take a minute now and take a bit of a detour to talk about what a function of several variables is and how to do calculus with it. So, up until now, you've basically learned about functions of a single variable, one variable. And usually you write them as y equals f of x, and then you just have some expression that involves x. For conic sections and some other things, you may have had your functions written implicitly, where you see x and y together, right? But um, in that realm, you still have always had f of x is the same thing as y, and y depends on x, right? So key thing depends. This is our independent variable. This is our dependent variable. A value for this can be used to predict a value for this. When we have a function of several variables, the game is a little different. So we have, for this one, z is equal to f of x and y. Right, and you notice here the function that we're looking at involves both x and y. So this is not the same as an implicitly defined one variable function, right? Because there are three variables in this whole equation, x, y, and z. Here, though, x and y are both independent variables, right? So x and y in this case would act like x in what you've learned before. And if we move up to functions of three variables, notice there are four variables in the entire equation. We have one dependent variable, w, and it's determined by three different independent variables, x, y, and z. All right, so when you look at your function notation, it basically tells you what your independent variables are. So in this case, x was the independent variable, y was the dependent variable. In this case, x and y are both independent and z is dependent. And in this case, x, y, and z are all independent and w is dependent. And an example, we have a function of two variables here that is something that's known as the Cobb-Douglas production function. Production function. Yeah, that could get really no. But anyway, in economics, that is a thing, and you'll find if you do take economics beyond just basics that there actually is quite a bit of calculus in it. But this is a function that we can use to determine production or output of a company based on a couple of inputs. So in this case, we're given this function of several variables, tells us what x and y are, and then it wants us to compare the production level. That's our dependent variable because it depends on the number of units of labor and the number of units of capital. All right, we want to compare the dependent variable for different sets of values for the independent variables. So when x is 1,000 and y is 500, all right, we get 100 multiplied by 1,000 to the 0.6 multiplied by 500 to the 0.4. And for that, I'm going to use a handy dandy calculator to get a value. But you see the idea here is that you're plugging in 1,000 for one of the independent variables and 500 for the other independent variable. And what we get out is going to be a value for the dependent variable, which in this case would be production level. Let's see, 0.6. And from that, put a squiggly since I'm gonna round. Get 75,785.83. And then the other set of values that we got was when x is 2,000 and when y is 1,000. So in this case, the setup is pretty similar. Right, and again, I'm going to use a handy dandy calculator for that one. Just change the numbers. Or not. All right, and when I used those numbers, I ended up getting 151,571.66. All right, so you see in that case, the production level was doubled when we doubled both variables, both independent variables. Okay, so now that we kind of have an idea of the input-output independent dependent variable interpretation, let's look at some algebra stuff. So when you find the domain of a function of a single variable, the thing that I usually teach is that you want to look for math no-nos, meaning things that you cannot plug in for your independent variable x. Here, we're looking at functions of 2 and 3 variables, right? So instead of just looking for no-nos that involve x, we'd have to look at no-nos that also involve y or z. Right, so when we write our domain out, or when we look to describe our domain, it's going to involve more than just x, right? And consequently, the range is still going to only describe what possible values we can get for our dependent or our output. So first thing, look at A. I noticed that there's an x in the denominator. Is there a number or a value for x that can never be in the denominator? Hopefully you said 0. So we know that x cannot be equal to 0. All right. The other thing I see is that we have an even root. All right, so with even roots, remember the inside has to be positive, otherwise you start dealing with complex numbers, which is not something we do in this course. But if you ever take complex analysis, you get to learn all about it. All right, so we know that the inside of that square root has to be greater than or equal to 0, which basically means that x squared plus y squared has to be greater than or equal to 9. Hopefully this looks a little bit familiar to you, right? If I have x squared plus y squared equals 9, that would be a circle with a radius of 3. Here, because x squared plus y squared is greater than or equal to 9, essentially we can only take points x, y that are outside of this circle and that do not have an x coordinate of 0. Fortunately for us, this is centered at the origin, so when x is 0, well, actually we should write that as well. So the domain is essentially going to be anything that is outside of this circle with radius 3 that does not have an x coordinate of 0. So basically, we can't be on the y-axis. We can't be inside the circle. We can be on it, we can be outside of it and not on the y-axis, but we cannot be inside, we cannot be on the y-axis. So graphically, geometrically, that's how you would describe the domain. When you were an algebra student, you learned how to write domain using a couple of different notations, right? You had set builder notation and you had interval notation. Interval notation doesn't really work when you have more than one independent variable, right? Because interval notation is kind of built on the assumption that you're only going forward and backwards, left to right. So we have to use set notation to write the domain mathematically. Specifically, because this is a function of x and y, my domain is going to consist of coordinates x, y, such that, and then we can write these requirements. So such that x squared plus y squared is greater than or equal to 9, comma, or and x does not equal 0. So if I wanted to write my domain in set notation, that is what it would look like. Now let's go on to our function of three variables. So a couple of things are going on in this one. We have a square root in the denominator. So because this is an even root, when I say even, I mean square root, fourth root, sixth root, eighth root, etc. Right? So not cube root, that would be odd, and those can be negative, right? They can have negative insides. Right? But for square root, or generally any even root, we know that this has to be greater than, so the inside of the root has to be greater than or equal to 0, except because that's in the denominator, it can't actually equal 0 because we can't have 0 in the denominator. So instead of putting the or equal to, we're just going to leave this as greater than 0. Now, if I were to rearrange this, I could add x squared, y squared, and z squared to both sides of my inequality. And then I would get x squared plus y squared plus z squared is less than 9, right? Or if you just added, you would say 9 is greater than that, which this is the same thing, just written in the flipped order, right? So hopefully we recognize what this is. So this was a circle with a radius of 3. This is a sphere with a radius of 3. And because this says less than, right, that means that we can take coordinates x, y, z that are inside of the sphere. Since there's not an or equal to, that would not include the sphere itself. So if a point is on the sphere, it's not in the domain of this function. If a point is outside of the sphere, let me kind of explain that a little more. So if a point is on the sphere, essentially its x, y, and z coordinate would work out to where this is 9 minus 9. So you'd get 0 in the denominator. If you were to take a coordinate that's outside of the sphere, right, x minus x squared minus y squared minus z squared would end up giving you 9 minus something bigger than 9. So you would end up getting imaginary values for your output, which again is not something that we deal with in this class. So instead, we are going to only say that we can plug values x, y, z in that satisfy this requirement, i.e. that are inside but not on the sphere, with radius 3 centered at the origin. And again, if I wanted to write the domain mathematically, I could use my set notation again, x, y, z, such that, and then I write my requirement, x squared plus y squared plus z squared must be less than 9. All right. So now let's look at another one. We want to find the domain and range and then describe the graph of this function. So remember when we see something like f of xy and then we see an expression involving x and y, we know that we can always write this as z equals the square root of all this stuff. Right? It's the same as when you would just write y instead of f of x in algebra, right? So if I wanted to get an idea of what this might look like, I would need to rearrange this to be only well, to be in closer to what we would call standard form when we're looking at, for example, quadric surfaces. One thing I do want you to note, though, is that this is just a square root, right? Positive square root, there's not a plus or minus. That'll make more sense when we identify what shape this is. So to get this in more of a standard form, I would need to square both sides. That gets rid of this root, and I would end up having a z squared, which looks a lot like some of the stuff that we dealt with in the last, well, section 11.6. So if I square both sides, this is where I am. If I move all of my variables to one side, this is where I am. And remember, when we looked at quadric surfaces, the right-hand side was either 1 or 0, right? So if I were to divide both sides by 16, divide every term in the equation by 16, then I would have a right side of 1, and I would be able to identify what kind of surface this is. So if I divide the first term by 16, 4 over 16 would reduce to 1 over 4. So we'd get x squared over 4. Okay. If I divide these other two terms by 16, it's just y squared over 16 and z squared over 16. And of course, 16 over itself is 1. Now, all of the squared, or all of the variables are squared. All of them are positive, and this is equal to positive 1. So if you remember your quadric surfaces from section 11.6, you'll know that that would make an ellipsoid. So it's kind of like a three-dimensional ellipse. Think if like the Zoloft guy in those commercials were three-dimensional. I couldn't think of something. Macaroon. Yeah, that's a less depressing example. Yeah. It's like a little macaroon. All right. But here's the thing. I mentioned earlier that we needed to keep in the back of our heads that this square root is positive and that there's not a plus or minus. And now that we know that the surface is an ellipsoid, right, that tells me that this is just the top half of the ellipsoid. So it's not the full ellipsoid, it's just the top half. So if I were to if I were to describe the graph, it doesn't tell me that I have to graph the whole thing, right? But it says to describe. I would say that this is the top half of an ellipsoid. Other details that we could figure out, we know where the center of the ellipsoid would be, 0, 0, 0, right? Because we're not subtracting anything from x, y, or z. And we also know that on the x-axis, we would have a radius of 2, and on the y and z axes, we would have radii of 4. Yep. But I don't want to write all that, so yeah. All right, so now that we've got that part of it taken care of, let's look at the domain, let's look at the range. So the domain, again, we want to look for our math no-nos, okay? So for the domain, notice we have an even root, and because we have an even root, we know that the inside of that root has to be greater than or equal to 0. So if I were to rearrange this, kind of like I did before, I would get 4x squared plus y squared is less than or equal to 16, right? Or 16 is greater than or equal to 4x squared plus y squared. Same thing. If I want to rearrange this inequality to make it, again, more of a standard form kind of thing, I could divide every term by 16. Remember, you only have to flip the inequality if you divide by a negative. Since we're dividing by positive 16, this stays the same direction. So we would end up with x squared over 4 plus y squared over 16 is less than or equal to 1. And if you remember your conic sections, which are pretty much the two-dimensional equivalent of your quadric surfaces, um, you would recognize that this is an ellipse, right? So it's an ellipse that has a x radius of 2 and a y radius of 4. So if I were to draw that, and again, we're centered at the origin because we're not adding or subtracting anything from x or y. Right, we would basically get this ellipse, except it's more symmetric and a little less like a human face. Okay. So essentially our domain is anything that is so less than or equal to would mean that we are inside of the ellipse. And if you think about the graph of this, that makes sense because this is essentially just what's on the XY plane in that graph, right? If I were to draw it out, you know that we would get something that looks like this. Very fast sketch. Right, so it's right. So essentially this is that rim of the semi-ellipse. Yes. So we can only take inputs that are in basically the floor of that three-dimensional shape. Okay, and that's our domain. Now the range are all the possible z coordinates that we could get. So in this case, let's think about some restrictions on what would happen. So if I were to plug in x and y so that this can be calculated, what are the possible values? I know that if I take the square root, like the positive square root of something, I always end up getting a non-negative number. Meaning if I chose the right x and y, I could make this 0, and the square root of 0 is 0. So that is a possible output, right? But if I plug in anything other than that, that doesn't make this become imaginary, I'm guaranteed to get a positive value. So all of the possible values of z that I could get are essentially anything greater than or equal to 0. And if we go back to our three-dimensional drawing here, z equals 0 would correspond to a point that's on essentially the floor of that semi-ellipse. If I get a positive value of z, then it's any of these other points that are on this surface, right? So if we think of it like a circus tent, the range is all the possible heights of points that are on the circus tent. So that's the range, that's the domain, and there we go. Yeah, I didn't write the domain as a set. So let's do that real quick. That's the set of all x and y such that x squared over 4 plus y squared over 16 is less than or equal to 1. Side note, you don't really have to write it in that form. If you wanted to write it like this or even like this, that would be perfectly fine. It's still correct. All right, but on some of the questions that you get about domain, like in your homework, it'll be more like describing it, right? So for example, the domain would be all of the points in the ellipse that we just drew here. And the range would be all non-negative values of z. All right. So another thing to note about functions of several variables. We've learned how to draw some of the three-dimensional shapes, and it's not even something I'm testing y'all over. Just being able to recognize and say, oh, this graph, this function makes this shape. Okay. But visualizing three-dimensional surfaces or can be really difficult. Visualizing four-dimensional surfaces is pretty much impossible. You can kind of sit around and philosophically think about what a four-dimensional solid might look like. Actually, it would be called a hypersolid. Um, but if you were to think spatially, that's just graphing would be a nightmare. So when we get to these higher dimensional functions, a lot of times we want to simplify it to two or maybe even three-dimensional plots that give us an idea of what the surface could look like. Right. So with functions of two variables, we use what are called contour maps. Right. And you'll draw these things that have a couple of different names. Your textbook calls them level curves. They're also called contour lines. And no, it has nothing to do with makeup. These are all natural. But essentially, what a contour line is, or level curve, is a line or a path that every point on that line or on that path has the same height. So if we're talking about functions of two variables, that basically means the same z coordinate, right? So there are a lot of examples out there in the real world of this. So if you have ever been much of a hiker like me, I love being in the mountains. A lot of times you'll see topographic maps of the layout of the land, right? And all of the lines that you see are essentially points on the mountain that have the same altitude. And if you watch the weather, sometimes they'll show you contour maps for temperature or for pressure. And in that case, like in the case of temperature maps, um, the lines represent areas, locations, exact coordinates where the temperature is the same, right? Also known as isotherms. Or on a graph of barometric pressure, it gives you coordinates, locations where the pressure, the barometric pressure in the air is the same, also known as isobars. Or if you're a physics geek and you've studied a little E&M, which will make way more sense when you're done with this course. Um, you may have seen something called potential fields, right? Electric potential fields. And those are essentially plots with a bunch of pathways where all of the lines represent points that have the same potential energy, right? And in physics, they break the ISO trend and call them equipotential lines. And those are some commonly encountered examples. So let's look at how we can actually draw these. So first we're given this function, f of xy is equal to the square root of 64 minus x squared minus y squared. Right, so if we were to rearrange this, remember f of xy we can always write as z, and that's the positive square root, so it's only going to give us the top half of a sphere, right, a hemisphere. All right, we can rearrange this, or we could rearrange this to see why it's a hemisphere, right? But to do what we're going to need to do, we're actually not going to, actually, why not? Let's do it. Let's square both sides. But I'm not going to do anything more than that. We're just going to square both sides. There we go. So essentially, this plot is going to be a bunch of two-dimensional graphs, okay? And the way that we figure out what those two-dimensional graphs look like are we take each of these values and we substitute them for z. Because remember, each graph is going to correspond to a set of points that have the same z coordinate on the three-dimensional graph. So if I let c be equal to, or if I let z be equal to 0, and here I put c because that's what textbook puts. So if you see that in your homework, just know that those are values that you should plug in for z. So if I plug 0 in, I end up getting 0 equals, I'll write it out here, c equals 0. 0 equals 64 minus x squared minus y squared. If I rearrange that, I end up getting x squared plus y squared equals 64. And if you remember your third grade math, you'll know that that's a circle centered at the origin that has a radius of 8. So I'm going to draw to the best of my abilities a circle. God, that's horrible. And the circle has a radius of 8. This is the curve that corresponds to c equals 0. All right, and then we want to do this for 1 all the way through 8. All right, so then with this other one, we would get 1 equals 64 minus x squared minus y squared. All right, this 1 squared is still 1. Yep. And if I rearrange this one, I'm going to add the x squared and the y squared to both sides. Then I'm going to subtract the 1 from both sides. So we would end up getting a circle centered at the origin that has a radius of square root 63, which is a little bit less than 8. So we're going to have basically a circle that is slightly smaller for c equals 1. And if I go on with c equals 2, we would rearrange and we would end up getting x squared plus y squared. I'll write it out. All right, so 2 squared, keep in mind we did square this, is going to give me 4. Okay. So when I rearrange this, I end up getting x squared plus y squared is 60. So that's even smaller. For c equals 3, we would end up getting x squared plus y squared is equal to 64 minus 9. That would be 3 squared, which gives us 55. So the square root of 55 is a little bit more than 7. It's definitely less than the square root of 60, though. So it's going to be even less than this one. And my cats are fighting again. Territorial. All right, so then for c equals 4, basically we would get, right, that would be 16. So we'd get 48, which will be less than 7. I realize this is definitely not drawn to scale. But the point is that we would end up getting these circles that get closer and closer to each other as we get higher values of z or c. Right? In reality, these should actually be much closer to each other. But I am not an art teacher, thankfully. All right. But anyway, this is our contour map. And one thing that you may be used to seeing in some of the real world examples that I pointed out are color schemes that go with it, right? So, for example, on a temperature map, they often make hotter temperatures closer to the red side of the color rainbow. Yay. And they often make colder temperatures closer to the blue, purple, violet side, right? So essentially, that would be like if I were to color each of these lines a different thing, or like color in between them so that For example, out here might be purple. Then I might have green, then I might get closer and closer to the red side, yellow, orange, red, right? And that might represent cold on the edges, hot on the center, right? If you were to ever get one of those thermal body heat superhero glasses things, right? You see like movement, body heat represented by that color, right? And that also kind of comes back to contour lines. Let's look at another one. So we want to sketch a contour map of the hyperbolic paraboloid given by z equals y squared minus x squared. So again, we want to start off with z equal to 0. And then we want to rearrange this to look like something that we know the graph of. So I'm going to start by adding x squared to both sides. So we get x squared equals y squared. If I take the square root of both sides, I get y is equal to plus or minus x. So y equals x and y equals negative x. On my contour map, that would correspond to y equals positive x, that's that line. Y equals negative x, that's this line. If I were to take another one like, say, z equals 1, right? This is the equation of a hyperbola. So you remember your hyperbolas, right? If you were to graph them, x squared minus y squared kind of made this shape. Y squared minus x squared, actually, yeah. Y squared minus x squared would make more this shape. Remember the hyperbola is the one where, yeah, the hyperbola is the one where you have two of these branches. If I were to continue this, right, like if I let z be equal to 2, I would still need to get this to a point where it matched the standard form for a hyperbola. So I would need to divide both sides by 2. I divide both sides by 2, I end up getting 1 equals y squared over 2 minus x squared over 2, which is going to be kind of like this shape, but it's going to be shrunk. It's going to be shrunk a little bit. And basically, if I were to continue plugging in larger and larger values of z, I would get hyperbolas that kind of continue on that trend. However, one thing that we haven't considered yet is what happens when z is a negative value, which is possible here. In this one, it wasn't possible because z is equal to the square root of something, which, as we said, was always positive. But here, z can be positive or negative. So we should also consider what happens when we have negative values of z. In this case, I would divide by -1 because I want this to make a hyperbola equation. If I do that, though, we end up getting +1 equals negative y squared plus x squared, which we can also write as x squared minus y squared. And that's going to make the other kind of hyperbola, right? The one that goes sideways. And if I were to pick higher or more negative values of z, like -2, -4, -6, -7, we would end up, again, getting that same pattern of hyperbolas. So we end up with a contour surface that looks like this. Pretty cool. If you go to Desmos 3D, you can get an actual picture of what the 3D surface looks like. Yeah, I'll write that here for you all so you can go and explore. All right. So with so the contour lines, contour maps, that is a way for us to visualize three-dimensional surfaces, functions of two variables. However, if we were to move up to functions of three variables, remember that would correspond to a four-dimensional graph. Because in three variable equations, we have x, we have y, we have z, and we have the dependent variable w, right? So there's not really a way for us to draw four-dimensional graphs. If you ever want to work on that problem, I'm sure you could find a research group that looks into that kind of stuff. But for us, instead, we're going to look at a way that we can kind of visualize, or at least look for patterns, because visualizing it would be kind of strange, um, in these functions of three variables. So level surfaces are what we would look at. So we did level curves, which were two-dimensional graphs to model functions of two variables. Now we'll do level surfaces to model three-dimensional graphs, or three-dimensional, three variable functions, four-dimensional graphs. Okay. So this one, remember f of x, y, z can also be written as w. And another thing I want you to think about is what would the range of w be? The range of this function. Well, keep in mind, you can plug any value you want in for x, y, and z. Right? The range or the domain for this function would be R3 instead of all sets of three coordinates, every point in three-dimensional space. The range, though, because we're squaring every number, the output has to be zero or something positive, right? So the range for W, so that's our domain, will be anything greater than or equal to zero because these are all squared, so there's no way for us to get negative values of W. With that said, the way that I would kind of get an idea of what the level surfaces look like is by plugging in different values for W. Kind of like how we did with level surfaces, we plugged in different values for Z. Here we'll plug in different values for W. So with that one, if I let W be zero, right, essentially that would just correspond to a point at the origin because the only solution to that equation is 0, 0, 0. Since you can't get negative outputs from squaring something. So we know that that would just be a point in three-dimensional space, kind of a bust. Now, if we let W be equal to 1, all right, we end up getting not quite a sphere. We could even say that it's an ellipsoid, right? Because remember, if you have 4 times x squared, that's the same as x squared divided by 1/4. So in the x direction, our ellipsoid would have a radius of square root of 1/4, also known as 1/2. And then the y and the z would have radii of 1. So in the x direction, that's 1. Here's a half. Right, and then the y and the z direction, we have 1. So x to z, we have that surface. Z to y, we have that surface. X to y, we have this surface. Okay. So far we have an ellipsoid, specifically a semi-ellipsoid, right? Actually, no, it's not a semi-ellipsoid, it's a whole ellipsoid. My bad. Yep, so it's both the top and the bottom part. If I were to let W be equal to 2, we would have to divide everything by 2 so that we get this in standard form. That would end up giving us basically another ellipsoid, but with different dimensions. So you have kind of an ellipsoid inside of an ellipsoid and a point inside of that. And if I let W be equal to 3, we would have to divide every term by 3 to make that into standard form. So that would give us another ellipsoid. So we have an ellipsoid inside an ellipsoid inside an ellipsoid. It's kind of like those little Russian dolls. I forget what they're called, where you have like a doll inside of a doll inside of a doll, or like those TikTok videos where they're doing like these trivia questions, and if you get one right, you get to open the little egg that has another egg inside. It's like that, but infinitely. Yeah. Um, so the level surfaces are ellipsoids. And there we go. So I've spent a while talking about some of the basics of functions of 2 and 3 variables, right? We looked at domain and range. We looked at inputs, outputs, independent and dependent variables. We even looked at ways to kind of look at graphs, even if they're not stuff that we can visualize, right? Using our contour lines, our contour maps, right? And our level surfaces for functions of 3 variables. So just remember, function of 2 variables is a 3-dimensional graph because the equation has 3 variables. Functions of 3 variables are 4-dimensional graphs because their equation has 4 variables, right? That's probably one of the more confusing things, but once you wrap your head around it, you won't have any trouble with it. Anyway, I'm going to make a separate video for the next part, which talks about limits. All right. Happy mathing.